Well, as promised, now that we're familiar with continuous functions, let's take a look at one of the important properties of continuous functions, which is encoded in the intermediate value theorem. This is one of those instances where we could also say that here's one of the very good reasons why mathematicians like to work abstractly, because the intermediate value theorem is a property that people had observed for polynomials and all sorts of other kinds of functions, and it turns out that continuity is the abstract property that makes it possible, which means as soon as you establish continuity, you know that you can apply the intermediate value theorem to a function, and you don't have to worry about the specifics of the function itself. Let's get to it now. Let's see. The intermediate value theorem says the following. You take a smaller than b, and you want f to be a function that is continuous on the interval ab. If f of a is smaller than 0 and f of b is greater than 0, or vice versa, so if there is a sign change on the interval, then there's got to be a 0 in the interval between a and b, so there's got to be a point c in ab so that f of c is equal to 0. Pictorially, that's pretty easy to see, actually. Suppose you come from below the axis and you're supposed to end up above the axis. Remember that continuous functions can be drawn in one pencil stroke, which means that no matter what you do with this function, no matter what you want to do to avoid this crossing, it's going to happen ultimately, because otherwise you would not be able to link up with the point on the right side. So this crossing here is unavoidable. Now, the theorem doesn't say anything about there being only one crossing. There could be several. There could be infinitely many even. Well, no, infinitely many. Yeah, it can happen, but you'd really have to be very careful in how you set up the function. Either way, okay, it doesn't say that there is only one 0, but there will be at least one 0 in the interval. And that's very useful, and in fact, you've seen it being used before anytime you were talking in algebra about finding where a function is positive or negative. Because what the intermediate value theorem says is that for a function to change from positive to negative, it either has to be 0 or there has to be a discontinuity, which for rational functions means it's undefined somewhere. So if we're asking for where a rational function is positive or negative, what do? Well, we find out where the function is equal to 0, and x squared equals 0 gives us x equals 0. We find where the function is discontinuous, which means for a rational function where it's undefined. We said x squared plus 3x minus 10 equals 0, and I think I did that with the quadratic formula. Yep. Negative b plus minus square root of b squared, which is 9 minus 4ac, so plus 40, because 4 times 1 times negative 10 is negative 40, and double minus gives you plus, and then divided by 2a on the bottom. So that's negative 3 plus minus square root of 49, which is 7 divided by 2. And then negative 3 plus 7 is 4 over 2 is 2. Negative 3 minus 7 is negative 10 over 2 is negative 5. So 2 and negative 5. And what do we do then? Well, basically, we have to look at the real line, and we can mark the 3 places where the function changes sign, which are negative 5, 0, and 2. And in preparation for graphing, which is actually still a bit down the road, but I would always recommend that you try to draw this to scale as much as possible. So these are the only points where the function can change its sign. That means the function will be either positive or negative in every one of these intervals that were defined by these cut points. Which also means that if we just check one point in every single one of these intervals, then the sign at that point tells us the sign of the function in the whole interval. Okay, so these checkpoints I usually try to indicate with a different mark, like something like a check mark here. So we need one here, we need one here, need one here, and we need one here. And those points, you choose them convenient. Well, convenient points, the point to the left of negative 5 is negative 6. A convenient point between negative 5 and 0 is probably negative 1. Convenient point between 0 and 1 is 1. And a convenient point to the right of 1 probably ought to be 3. And now you just take these numbers and plug them into the function. And that's a little bit of mental arithmetic, but nonetheless, we can do that. Let's see. I claim that the function is positive at negative 6. Well, let's see. Negative 6 squared is 36. We don't even really have to remember that it's 36, because that just tells us our numerator is positive, and that's what we're after. And in the denominator, we've got negative 6 squared being 36. Okay, remember that. 3 times negative 6 is negative 18. 36 minus 18 is 18, so that's good. Minus 10 is 8. 8 is positive, and that's why the function is considered, or that's why the function is positive to the left of negative 5. Do the same thing with negative 1. Negative 1 squared is 1, but more importantly, the numerator is positive. Negative 1 squared is 1, minus 3 minus 10, that's negative 12, so positive divided by negative gives us negative. 1 squared is 1, 1 squared plus 3 is 4, minus 10 is negative 6, so we get positive divided by negative. Function is negative. And 3, well, 3 squared is 9, 3 squared plus 3 times 3 is 18 total. Minus 10 is 8, that's positive, so positive divided by positive is positive. And that tells us that our function is positive from negative infinity to negative 5, negative from negative 5 to 0, negative from 0 to 2, and positive from 2 to infinity. And sometimes you just want to write that out as a sentence. I didn't have enough room here, so I don't think I did that. No, I didn't. Double check. You can always graph the function. And, well, you realize, okay, here it's positive up to negative 5. It's negative from negative 5 to 0 and from 0 to 2. And it's positive from 2 on. So it's verifying what we have worked out. Positivity and negativity is, of course, something that we're interested in when we're finding the domains of functions, like the function x over square root x plus 4x minus 3. Well, what can go wrong with the domain of a function? You could have a division by 0, or you could have negative signs under the radical. And so here, in order to find where stuff under the radical is negative, we have to find the zeros of this anyway, and those will also be the zeros of the denominator. And so, well, the zeros are negative 4 and 3, and we need to know where x plus 4 times x minus 3 is positive or negative. And we do the same thing. A number line, we mark our two cut points, negative 4 and 3. We find ourselves 1, 2, 3 checkpoints. So let's see, negative 5 would be convenient here, 0 would be convenient here, and 4 would be convenient here. And now we just plug that in, but not into the function itself. We're now only interested in the sign of x minus 4 times x plus 4 times x minus 3. So let's see. Negative 5 minus 4, negative 5 plus 4 is negative. Negative 5 minus 3 is negative also. Negative times negative is positive, so it's positive here. 0 plus 4 times 0 minus 3, that's positive times negative, that's negative. And 4 plus 4 times 4 minus 3, that's positive times positive, so it's positive here. And that means the function is defined from negative infinity to negative 4, and from 3 to infinity. And the domain, therefore, is negative infinity to negative 4, union 3 to infinity, with negative 4 and 3 being excluded because we divide by that. If they had been included, if this had been the reciprocal, let's say, then we could have included negative 4 and 3 in the domain. And again, we can double check that. Negative 4 to 3 in a plot of this function, which has a branch here and a branch here and nothing in between, that is excluded from the domain, just as our computation predicted. Okay, the part that I had promised was the Intermediate Value Theorem. That's also the title of the presentation. That's what comes now. Because in order to solve equations approximately, we can use the Intermediate Value Theorem to implement what is called the bisection method. The idea is very simple. You are given a continuous function on an interval, and f of a and f of b don't have the same sign. That means by the Intermediate Value Theorem, we know that there is a 0 in that interval. Okay, the task is to determine numbers L and R, left and right, so that there is a 0, a c with L smaller c smaller r, so that f of c is equal to 0. So there is a 0 of the function between L and R. And so that the difference between right and left is less than a given tolerance t, because really any time, for example, if you zoom in on a 0 of your function on a graphing calculator, let's say, you may have done that before. Basically what you're doing is you're giving it left and right bounds, and you're graphically making sure that the 0 is still within that interval. Okay, the algorithm then is quite simple. You take your left bound to be A, your right bound to be B. You check if the difference is smaller than the tolerance, and if it is, then you stop, of course. Otherwise, you just find the middle of that interval, and you determine the sign of the value of the function in the middle. And if the left and the middle have the same sign for the output, then your new left endpoint will be the middle, and you continue with step 2. If your right endpoint in the middle give you the same sign, then you set your new right endpoint to be the middle, and you continue at step 2 also, and you just keep doing that until the difference between those points is smaller than the tolerance. Okay, that looks a little bit abstract, but it's actually a pretty common description of an algorithm. If you do more in programming, you'll see stuff like this certainly more often. Let's see how it works. Okay, when the algorithm terminates, L and R will be as desired. Let's see how this thing works. We're looking at the solution S of the equation tangent x equals 2 plus x in the interval from 0 to pi over 2. And we want to find left and right bounds L and R so that L is smaller than S. That should be S, not Z, but hey, it's just a name. And so that R minus L is smaller than 10 to negative 2. Okay, well, here's the function tangent x. Here's the line 2 plus x. And, well, here is the intersection, and so this should be the solution. Here's another intersection, but that's outside the interval 0 to pi over 2, which ends right here. So we're really only interested in this one. Okay, how can we work that out? Well, here is what we get when we focus on the interval from 0 to pi over 2, and we really get just one intersection. The intermediate value theorem talks about zeros, but a standard way to solve equations using the intermediate value theorem is that we simply bring everything to one side. So here we could look at the function 2 plus x minus tangent x, which is what you get when you subtract tangent x on both sides. And then our solution really is a zero of this function. Okay, so what do? We set ourselves up with a table. We've got your left point and your right endpoint and your center point. And aside from the point, we'll also record the sign of the function for each one of them. And in a separate column, we also record the difference between right and left, because when that's shorter than 10 to negative 2, which is 0.01, then we're going to stop the algorithm. Okay, so we start with A being the left endpoint, L being the endpoint A, which is 0, R being the endpoint R, B, which is pi halves, which is approximately 1.5708. And we know from the picture on the previous slide, function is positive at 0 and negative at 1.5708. That's what we're also seeing here. Difference is, of course, not below the tolerance. Okay, we find the center point, and of course we're going to use a calculator for that. And then we don't need to draw the graph. We could just compute it, but we realize that the function is positive at the center point. What did the algorithm say? And here we can also see why we're using the algorithm. If your function goes from positive to positive on an interval, then there need not be a 0 on that interval, and here there isn't. But if your function goes from positive to negative, then there will be a 0 here. So this guy will become our new left endpoint. So first of all, we just record that row, and now we get a new left endpoint. Right endpoint stayed the same. We still have sign change positive to negative. This is what it looks like now. We find the center point, which is 1.1781. Okay, yeah, I use a calculator, and the function is positive there. Good. That means this guy here will be our new left endpoint. This will remain the right endpoint. Okay. Record the row. Left endpoint, right here, right? We'll find the center point, which is 1.3744, and the function is negative this time. Okay, so this time we've got to change from positive to negative on the left side. So now this will be our new left endpoint, and this will be our new right endpoint. Right, okay, just record, and you can see now the left endpoint is here, and the right endpoint is this one. And again, this time it's actually kind of hard to see. Well, the center point is 1.2763, and apparently the function is barely negative there. So left endpoint will be this one, right endpoint will be that one. First of all, just keep recording stuff, of course. And of course, you're going to do this row by row. I just wanted to flash the pictures, and so that's why my rows are jumping a little bit. Here's our left endpoint, here's our right endpoint. We find the center, function is positive at the center. So that means now here's the left endpoint, here's the right endpoint. We realize apparently it's got to be positive in the center. Here's the center, and yes, it's positive. Okay, so we get a new left endpoint, we get a new right endpoint. And the center point ought to be positive again, 1.2640. Function is positive there. Okay. Center point becomes a left endpoint, right endpoint is still the right endpoint. You can see by now the tolerance is getting pretty close. And well, so this time function is still positive at the center. So we record that row. This is our new left endpoint, this is our new right endpoint, and we can see that now the difference between these two endpoints is 0.0061, which is smaller than 0.01, and that means we really don't have to worry about this anymore. We have reached the desired tolerance, and so our values, L and R, that we would record are 1.2701 and 1.2763. We know that the solution will be between these two. If we're interested in accurate digits, we would record the digits that won't change anymore. We would know that the solution starts with 1.27. That's what you also often get reported by your calculator. Your calculator, even if you've got a root finder, and you probably do, I mean, these things do all sorts of things, what it gives you is an approximation. What it does internally is either some kind of bisection method or something like a calculus-based method called Newton's method, but either way, the digits that you get are basically the digits that don't change in an approximation where eventually internally we still only know that the zero is between something where the digits are a little lower and something else where the digits are a little bit higher. Okay, so we've reached our tolerance, and right, we're finishing with a little abstract result that is needed in calculus mainly as an existence result. And that is, if you've got a real valued function and D is a subset of the domain, then the value y sub m is called the absolute minimum value of the function in the domain, if and only if there is an x, so that f of xm is ym, and so that for all points in the domain we have that f of x is greater or equal than f of xm. So that would be a point so that the function never takes on a smaller value and the value itself is being assumed. Similarly, the value y sub capital M is called the absolute maximum value of the function, potentially in a domain, if and only if there is a point in the domain where the maximum value is assumed, and for every other point in the domain, we have that the function doesn't exceed this maximum value. And a value that is the absolute maximum or the absolute minimum is also called an absolute extremum. So that could be either or. It could be an extreme high or an extreme low. And the theorem is that if you've got a continuous function on a closed and bounded interval AB, then that thing will really assume its absolute maximum and minimum values. These kinds of values are important in any kind of optimization, because optimization will always be the getting the highest possible output or the lowest possible losses and so on. And continuity just guarantees that there really is a place that realizes these output values. However, and here's where we're going to argue abstractly, the hypothesis of continuity is required. Take a look at this function. It looks monstrous, but it isn't that bad. Basically, it's a straight line from -1 to 0, and it's x plus 1. So it's going to be above the x-axis, slope 1. From 0 to 1, it's 1 minus x, so it starts at 1 and goes back down with slope -1. And it's 0 at x equals 0. Looks like this. Well, that's a function where you would say, oh, well, we want the maximum to be 1, right? That's what it is. But the function is not continuous there. The function is one of those annoying removable discontinuities. But we're not talking about removal here. We have to look at the function as it is. And being as it is, the function is not continuous, and it doesn't assume an absolute maximum value because the output values get arbitrarily close to 1, but they don't hit 1 itself. Okay, so that is basically one of those examples that says, yes, as we are working with abstract theorems, we have to be careful with hypotheses and the like. But the main thing that I hope has happened in this presentation is that you've seen that even though continuity is an abstract property, first of all, in algebra, it's very likely that you've already worked with the idea of the intermediate value theorem for special cases like rational functions, stuff with roots, and so on, as you were determining whether a function is positive or negative, where a function is positive or negative, and also when you were determining domains. I hope it's also been driven home that this kind of abstract stuff has applications in numerical analysis, for example, because the intermediate value theorem led to the bisection method, which is a numerical method. And then finally, we talked a little bit about abstract stuff, about an existence theorem for extrema, which will certainly be in the background of an applied class as calculus is, but it is something that simply just guarantees that we're not on a wild goose chase when we're looking for extrema and optimization. Alright, that's it for the abstract stuff. I think this module finishes out by talking about limits at infinity, so I'll see you there.